Over this set of videos, we will define the impulse imparted to an object by a force acting over time, then derive the impulse momentum theorem, define the momentum of an object, and express Newton's second law in a new way in terms of momentum. So, how can we quantify the cumulative effect of a force acting on an object over time? Note that Newton's second law gives us the instantaneous acceleration based on the instantaneous net force, but of course we're often interested in how a force affects an object over time as it continues to act. So if you want to know the cumulative effect of the force acting over time, here is a way to quantify that. What we can do is take the time integral of that force from time 1 to time 2, and we call this integral the impulse. The impulse imparted to an object acted upon by that force between time 1 and time 2. So this is the impulse imparted by that force. The force is a vector, so the impulse will be a vector as well. This is a vector equation, so of course it can be represented as separate equations for each component. So the x component of the impulse equals the time integral of the x component of the force, and so on. Unit-wise, we see that if this is force times time, then that is newtons times seconds. The SI unit for impulse is newton seconds, not newtons per second, newtons times seconds. We usually say newton seconds. Why the letter J for impulse? Well, in the old Latin alphabet, in Latin, a J and an I were indistinguishable letters. So it's actually an I for an impulse, but often written as a J. So, okay. This equation suggests to us that if we were to think of the average value of the force, average value of a force over some time interval is given by the integral over the interval. So comparing these two expressions, we see that the integral of the force acting over time, the time integral here, is equal to the average value of that force over the interval times delta t. So we can replace this with average force times delta t to express the impulse this way. So our impulse equals the average force over that time interval times the duration of that time interval. And this equation makes it more clear, this vector equation makes it more clear that the direction of our impulse vector will be in the same direction as the average force over that time interval. So impulse and average force are always parallel to each other. Okay, so let's look at think of like some example scenarios here where we might care about impulse, or we can apply this impulse idea. Suppose we just have, say, a ball that's been tossed in the air and is following a projectile trajectory with only gravity acting on it. So it is in free fall, subject only to gravity. And here is time where the ball is located at time 1 and time 2. We could graph the y component of the force on the ball versus time, and the x component of the force on the ball versus time. So the y component of our force is the constant minus mg. So there's our constant minus mg. And so from time 1 to time 2, the integral of our force function is represented graphically by the area between our function and the zero axis here. So that area there, that rectangular area, represents the y component of the impulse imparted by this force of gravity from time 1 to time 2. Note that it would be a negative value here since the area is below the zero axis. Okay, so gravity gave us a negative impulse from time 1 to time 2 in the y direction. But there is no component of the force in the x direction. So there is zero impulse in the x direction from time 1 to time 2. But we usually think of impulse in the context of collisions. So let's consider that. Okay, here. Here I've got, say, a ball bouncing off of the floor at 5 moments in time. So here's the ball coming down. Here it's contacted the floor and is compressing a little bit. Here it's maximally compressed. Now it's uncompressing, and here it is bouncing on the way back up. So we've got a time sequence here. I've indicated the center of mass velocity of the ball with the blue arrow in all four. So we see it's going fastest, then it begins to slow down as it starts to contact the floor and compress. And as it contacts the floor, there will be a contact force from the floor on the ball, indicated in red here. And that contact force is going to grow in strength the more compressed the ball is, and then decrease in strength as the ball uncompresses as its velocity reverses direction and it heads back up. Now the ball will compress, but the floor will compress as well because no surface is completely rigid. It can be hard to tell by eye that the floor is compressing as well, but it is. Basically, every collision between two rigid bodies involves some slight depression, at least some slight deformation of the bodies. So a collision between a block and a spring is a good model for pretty much any collision. Everything is springs. This ball is spring-like, and even the floor here, the surface, will compress in a spring-like way. So here we've got a block sliding in, let's say on a frictionless surface to contact this spring. Again, blue is its velocity vector. Contacts the spring, compresses it, and as it compresses it, the spring exerts a contact force on the block, that's in red, getting bigger as the spring gets more compressed, and the contact force getting smaller as the spring gets less compressed, and the block is released and it heads back out to the right. So either of these in either of these scenarios, the contact force on the ball or on the block, graphed versus time, would look something like this. Here's kind of a generic force versus time graph for a short duration collision in which there is zero contact force before the objects are in contact. Say here and here, no contact force, it's zero. At time 1, the two objects make contact, and as they begin to compress into each other, the force increases up to a maximum, then drops back down to zero as they uncompress. So the force peaks at this moment of maximum compression and then decreases again, and then the force goes back to zero once the objects lose contact. There we go. So the integral of force versus time, the integral, the area under this curve here would be the impulse, J, imparted to the block or the ball by that force surface. So this represents the sort of cumulative effect of that force acting over time.